Okay, as promised, up next is Young's double slit experiment. Now, this is just a very special case of the interference that we've been looking at, so hopefully this should all go pretty straightforward. I am, however, going to show you some interesting things to start with, just things to get your brains going. So, we've looked at diffraction and we've looked at interference. Now, diffraction, you know, is where light spreads out after passing through a gap or around an obstacle. And if I get diffraction from lots of points all at once, then I get interference patterns. What's interesting, though, is if I send light through a single gap, I still get a fringe pattern, I still get an interference pattern, and it looks a bit like this. So, as you can see, this is laser light that's just gone through one single slit. I will show you this in the lab, by the way, so you don't think I'm cheating here. But we get one big bright fringe in the middle. There's clearly a dark bit, then a bright fringe, dark, bright. So we've got max min, max min, max min, max min. So we've got this interference pattern kind of thing from before. And the central fringe is much brighter and approximately twice as big as the others. If we plotted a graph of intensity against position, it sort of looks like this. So that's actually quite interesting, right? If any of you can tell me why that happens, or has any suggestions or thoughts about why that happens, I would love to hear them. It's not on the syllabus, it's just interesting. There's always a little bit more to what's going on than you think. So that's just for you to have a little think about between now and when I see you. Now, I already showed you the double slit. I'm just going to show you how it changes from having a single slit to a double. You can see we've actually still got this underlying big and then smaller bits when I get to the double slit. It's just that then those bright spots are further divided up into their fringes as well. That's what we call these bright spots, by the way, fringes, and fringe spacing means how far apart they are, just so you can get used to the language. So that's what we've been looking at. So, this experiment with light was first done quite some time ago, and at the time it was a very, very important experiment because there was a lot of debate about what light was. Was light a particle or was it a wave? And I told you earlier that diffraction is something that only waves do. So, an experiment that showed light diffracting and then interfering would be an experiment that also showed that light was a wave. So this was originally demonstrated in 1801 by Thomas Young, and this was really, really important because it showed interference, it showed diffraction, and it showed it was wave-like radiation. At the time it was a really big thing, and there was a lot of debate about it. A lot of big names weighed in on it, and not always. I mean, science is a funny thing. Sometimes the best facts or the best evidence, the theory with the most proof behind it is the one that's believed, and sometimes the theory that's suggested by the person who has the biggest name. For instance, Isaac Newton is believed, even when he's wrong. So this was just something that was part of that debate, which we will talk about in a little bit more detail later. It's something that comes up again. But anyway, this was the layout, the experimental equipment that Thomas Young had. So he had his lamp, then he had a colour filter, then he sent all his light through a single slit. It then carried on until it went through a double slit, and then carried on until it went to a screen, and it was on the screen that the fringes of light were seen like this. So we're going to talk about exactly why he had all these different bits in his experiment and in his setup, because they're all there for a good reason. Okay, so first of all, the light source, it needs to be monochromatic, so one colour, one frequency, one wavelength. And you can do that by using a colour filter with a white light, which is what he did. Other options are using a light source that's already monochromatic, so a laser we've already talked about. Another example would be a sodium lamp. The single slit. The single slit is there to make the light coherent. So it basically just cuts down on all the other bits of light that are coming in from slightly different points on that light source so that they're all going to have a constant phase difference. Now you don't need the single slit if you're doing this with a laser. Next are the double slits, which obviously we need because we're trying to do an experiment where we send it through two sources. They provide us with two sources of light. It's like having two identical light sources next to each other. Typically they are about 0.1 of a millimetre wide and separated by about half a mil. We then have a gap between this, the double slits and the screen, and that's typically about a metre. The reason we have that big distance is so that the fringes are far enough spaced out that we can see. If you have a shorter distance, that's fine, but then maybe you might want to use a microscope so you can actually have a good close look at what's going on. Okay, so our interference fringes then. This is what they look like. We get bright, dark, and we get this intensity spectrum as well. So it's much more intense in the middle, and the intensity drops off as we go from side to side. So the brightness of the bright ones is smaller at the edge, and it's much clearer in the middle. So bright fringes are formed where the light from one slit is reinforcing the light from the other slit. So this is that interference thing. It's specific, and it is where we get reinforcement. So in terms of phase, that means that at the bright fringe, the light from both sources is in phase with each other. Other way of putting it is the path difference would be equal to a whole number of wavelengths. So none, 1 lambda, 2 lambda, 3 lambda, so on and so forth. Dark fringes, on the other hand, are caused by cancellation, and that's where the light from the slits is 180 degrees out of phase or completely out of phase. Alternatively, we could talk about the path difference having an odd half number of wavelengths, so half a wavelength, 3 over 2 wavelengths, 5 over 2 wavelengths, and so on and so forth. So that explains the formation of this interference pattern in terms of both path difference and phase difference. Now, there was an equation that came out of all this study, because, you know, physicists, we like our equations, and the equation was as such. It said that the fringe spacing, which we're going to call A, is equal to lambda d over x. So, x is our slit separation, d is the distance from the slits to the screen, and lambda is the wavelength of the light. So if I know what wavelength of light I'm putting in, well, actually the wavelength is the thing I might want to find out. So if I put some light through a fringe spacing that I know of, through a slit separation that I know the distance from the slits to the screen, and I measure the fringe spacing, then I can calculate what the wavelength of light is. So this gives us a way to directly find and calculate the wavelengths of light from these diffraction effects, which is very, very useful. Now, I will say the two that you are likely to forget which way around to go are A and X. So A is the fringe spacing and X is the slit separation. But algebraically, it doesn't matter if you can't remember which is which because of where they are in the equation. So don't agonise about it if you can't remember. When you should know it, I'm not saying don't learn it, but if it comes to the exam, you're faced with this equation and you can't remember if A is the fringe spacing or if A is the slit separation, just stick one in one number and one in the other, and it won't matter because it will come out with the right answer just because of where they are in the equation and how they're related to each other. Okay, right, that is it on Young's double slit experiment. We will do some calculations and we will have a little bit of a play, and if you're very lucky we might even measure the wavelength of visible light, which is kind of a cool thing to be able to say we can do, right? Okay, so that is it for today. Remember, any questions, ask when you see me.